Alright, so time for some examples of testing for continuity with limits. So this was our basic definition of continuity, our new fancy definition, besides just saying, oh, you can trace the whole graph without picking up your pencil. Okay, and don't forget that if the limit exists at a value a, that's only because the limit from the left of that value, or sorry, as we approach from the left, has to equal the limit as we approach from the right. Okay, so that's the implied breakdown of that. So again, we really have 1, 2, 3 checkpoints we're looking at for each of these questions. We also discussed the type of discontinuities that you come across. One type is removable, and this is only going to happen if you have a hole in the graph. And the reason this happens is because f of a is undefined. The non-removable discontinuities include jump discontinuity and infinite discontinuity. Okay. And these jump occurs whenever the limit from the left does not equal the limit of f of x as x approaches a from the right. And then infinite means everything's wrong, right? Same idea as up here, and also f of a is undefined. Okay, so when we're checking to see these things, we're looking at that definition, seeing if all three parts are met, and if they're not, based on which part isn't met, we're able to determine if it's a removable discontinuity or non-removable. So for our first example, let's just practice identifying points of discontinuity graphically, because that's kind of the easiest place to start. And then, as a result, the intervals over which the function is continuous. So basically removing those discontinuities from our possible intervals, and what's left is where it's continuous. Okay, so find the points, aka intervals, at which the function below is continuous. That's just a fancy way, a lot of times, not always, of asking for the domain of the function, because our domain is where the function's defined. Okay, so it's going to be continuous over the interval. Okay, so we're starting, again, it's only from 0 to 5 that we're checking, so our interval has to start at 0. We can at least get that. And because they're not using the little equal parts here, I'm going to put a curved bracket around 0. Alright, so we're on 0, we're traveling until we get to 1. And at 1 we have a removable discontinuity or a hole. So that's going to be our first break. And then we're going to use that union symbol to continue on. So picking back up at 1, and then going, as we get closer to 2, we're going up to infinity. So we're not actually going to reach 2, we're just going to approach it. Okay, and then we're going to pick back up on the other side of 2. And we're coming back down, we're all good until we get to 4, where we have a jump discontinuity. And then after that, we're good until we reach 5, which again is not included. So picking back up with 4, going to 5, not including. So this would be the intervals at which the function is continuous, and also it would be the domain of our function. Okay, so again, let's list these discontinuities. The first discontinuity is occurring here at 1, and it's a hole, which is removable. Our next discontinuity is here at 2, because we had to jump over 2 because of that vertical asymptote. So that means it's going to be non-removable. And you can still put like vertical asymptote and hole. That's probably a really good thing to practice. But the overall answer is just, is it removable or non-removable? And then the last one, as we approached 4, there's this gap here. Okay, and we call that gap a jump discontinuity. So that's going to be at x equals 4. And jump discontinuities are also non-removable. Alright. Oh, sorry about that. Okay, now let's go to the next one. Okay, so let's get more formal. Let's actually use the definition of continuity to determine if the function is continuous at x equals 1. Now, we just talked about how we already know this is discontinuous, but I want us to be able to use the definition correctly in order to prove it using limits. So the first thing we'll look at is the limit as we approach from the left. The limit as we approach from the left at 1 is giving me a 1. Now we're going to look at the right-hand limit. And as we're approaching from the right, we're also getting a 1. So far, it looks like it could be continuous, although our eyes tell us we already know it's not going to be. So this tells us that the overall limit as x approaches 1 exists, and that it's equal to 1. So then the last part of our checklist is to see what is the actual value f of 1. Okay? And the actual value for f of 1 is up here, and it's at 3. Okay, so did the limit value match the actual function value at 1? Well, in fact, it did not. So we got our very surprising conclusion that it was not continuous, since the limit as x approaches 1 of f of x is not equal to f of 1. Okay, same graph, different point. Again, using the definition, this time looking at x equals 2. So we'll start with the left-hand limit first. And as we approach 2 from the left, we're going up off the graph towards positive infinity. Then the right-hand limit. Okay, and as we're coming from the right, we are still going up off the graph. So technically, we could say that the limit as x approaches 2 of the function is infinity. However, remember, in the back of our minds, we're thinking that means the limit doesn't exist. Okay. Then we're looking at the next part of the criteria, which is what is f of 2? And if we go to the graph, there is actually nothing at f of 2. There is no defined value. So f of 2 is undefined. Now here's the real question of the night, or day, whenever you're watching this. Does the do not exist equal undefined? Well, we already know from our previous work with this problem that it is not continuous at 2. So just because a limit doesn't exist doesn't mean it's equal to something else not existing. It just means it's not going to be continuous there. Those are not the same things, technically. So we'll conclude it's not continuous since the limit as x approaches 2 does not equal f of 2. And pretty much you know this is going to be the case going forward. Anytime you have an unbounded limit, there's no way it's going to equal the output of a value because it's not a number. So you'll start getting the hang of these a lot faster the more you do. However, if this is some sort of AP open-ended question, you would still want to go through all these steps to prove the reason you're putting this as your final answer. Okay, same graph. Now we're looking at x equals 3. Let's approach from the left. Okay, as we're approaching 3, I'm getting a 1. Now from the right. Okay, again, and I'm getting a 1 from that direction as well. So far we would say the limit as x approaches 3 of the function is giving us a 1. So now let's actually look at what f of 3 is. Okay, if I go to 3, I have a defined value at 1. Finally, this is an example of proving a function is continuous at a point. So it is continuous at the point x equals 3, since the limit as x approaches 3 of f of x is equal to the actual outpoint of f of 3. Okay, and all of them equal 1. Sometimes people add that in like that, putting an extra part, and some people kind of write it separate. Doesn't matter to me. Okay, last one with this graph, I promise. Okay, so looking at the limit as we approach 4 from the left, boop, I'm getting a 2. And as we approach from the right, I'm getting a 1. So this is one that doesn't take very long to figure out. It's not going to work because we're just getting two completely different one-sided limits. So for this example, we could just go ahead and conclude that it's not going to be continuous since the left and right-hand limits are not the same. Okay, so what if you don't have a graph? Let's talk about algebraic stuff. So same idea. We're going to do the left limit and the right limit. But first we have to figure out if there's a point we need to test in the first place. So with rational functions such as this one, the denominator is where we would get a point of discontinuity if there is one. And we should always check to see if that value in the denominator will cancel with something in the numerator or if it will not be able to be changed. AKA, let's simplify this. So in this case, it actually will cancel with something in the numerator, which means we have a removable discontinuity at x equals -2. So that means that the function will be continuous everywhere else on its domain, but x equals -2 is not part of that domain, so that's where we need to check. Okay, so we already know it's not going to be continuous, but we're proving it with the definition. So we're going to approach -2 from the left and from the right. Okay, and from both directions we're going to be left just working with the remaining expression after we cancel the factors of 2x minus 3, or 2 times -2 minus 3. And that would be the same from both directions. So in both cases we're getting -7, so the limit as x approaches 2 of this function is -7. So the last thing we would be checking is the actual value f of -2, and because this one is a removable discontinuity, that's where our issue occurs. So with the use of the, of the definition, it would be that particular requirement that is not met here. So we would conclude that it's not continuous since the limit as x approaches -2 of the function is not equal to f of -2 of the function, and you would show all this work as your backup for that conclusion. Okay, so piecewise are a little trickier because you really have to think about where you might have discontinuity. So for this particular function, the first thing I usually check is like where it's kind of broken apart at. But if I plug a 1 in, which is what it would be approaching, I'm still getting a 1 out, which matches what is defined out for the next piece. So it looks like these actually would meet up. So it's not going to be 1 that I'm concerned with. So that's when you look at which x values are where. So this first piece is for x values less than 1. Well, this is a rational function, so I need to be careful about anything in the denominator. And what cannot be in this denominator is a 0. And since that's part of this domain, that's where I'm going to check for discontinuity. So again, since denominators can't equal 0 and this denominator is x squared, that tells us that x cannot equal 0. And if you look at it, we can't simplify it. It's not a whole. So this means that it's a non-removable discontinuity. Okay, and this is because there's a vertical asymptote at 0 for that first piece of the piecewise. Okay, so for both of these left and right limit questions, we're looking only at this piece, and there's a vertical asymptote there, so remember this is where we kind of like do kind of test numbers to plug in. So something really close to 0 but to the left, well, when I think about that, that's going to be some sort of really tiny negative number. However, we are going to be squaring it, so no matter what it is, it's going to end up being a positive 1 over something positive, which means this guy's going to go to positive infinity. And if we're looking at values that are slightly to the right of 0, it's going to be a really tiny positive number squared, which is positive, and that 1 is positive, so again, positive over positive gives me positive infinity. So the limit as we approach 0 of this function is going to give us positive infinity. So then we check the actual point f of 0, and again, that's going to be undefined. We can't have a value if there's a vertical asymptote there. So our conclusion would be it's not continuous since the limit as x approaches 0 of f of x is not equal to f of 0. Last but not least, part C of example 3, another piecewise, but notice this time we've got something linear and something quadratic. Both of those are continuous over all of their domain, so there shouldn't be any asymptotes, holes, or jumps. But the jump I should probably check first by plugging in a 1 for both of them. So when I plug in a 1 for each piece of the piecewise, they're both meeting up at a y value of 1, so there will not be a jump discontinuity. Okay, so now we're basically going to do that in a more formal way. So the x value of 1 is our point of interest. We're going to approach it from the left, which means we would use this first function, which we kind of already did the work for right here. And then the limit as we approach 1 from the right is going to be the second function. And again, we've done the work already right here. And we already said that for both we're going to get a 1. So the limit as x approaches 1 of f of x is equal to 1. So now we just check what is f of 1. Well, f of 1 is going to be where the function has the equal part. So we would plug it in for 1 squared, which equals 1. So our conclusion would be that the function is continuous since the limit as x approaches 1 of f of x equals f of 1.